Okay, hello everybody. Today I'm going to talk about the first lecture for Financial Engineering and Risk Management by Columbia University. We're going to talk about the distributions. Let's get started. So a discrete random variable, hopefully we know what that is because there's no definition here, but the cumulative distribution function CDF of x, a random variable xi, is defined by f of x, is probability that x is less than or equal to x. So what does that look like? Generally here, negative infinity, infinity, and then we have right here 0 to 1. And so it starts at 0, and at some point it goes up to 1. It might not look like this, and it never gets above 1. So something like that. A discrete random variable x has probability mass function PMF P if P of x is greater than or equal to 0. And for all events A, we have probability x is in A is equal to the sum that P of x, sum over all x and A, P of x. So what does this look like? Let's do an example. So suppose you're rolling a 6-sided die. These are the possibilities, 1, 3, 4, 5, 6, and then each of these is equally likely with probability 1/6. So then in this case, P of x is equal to 1/6 for any x, for all x in 1 to 6. Sorry, it should be square brackets, 1 to 6. One interesting thing to note here that he didn't note is if A is just one element little x, then the probability of this is just equal to P of little x. Therefore, so basically this holds true. So then P of x in A is equal to probability, sum over all x in A, and this is big B of x is equal to x. I guess I also just thought of the question, what if x does not have, is it possible for x not to have a probability mass function? I think so. I think if, well, I'm not sure actually. I'll have to come back to that. Okay. The expected value of a discrete random variable x is given by expected value of x is equal to sum of xi, P of xi. So this is just 1 times 1/6 plus 2 times 1/6, etc. So the expected value. And then the variance is defined by that, and these two are equal. Okay, the binomial distribution, we say x has a binomial distribution if P of x equal to r is n choose r, P to the power of r, 1 minus P, and minus r. For example, x might represent the number of heads and n independent coin tosses where P equals probability of head. The mean and variance of the binomial distribution satisfy expectation of x equal to np. So I wanted to prove this. This is very similar to the proof for Poisson. Let me check that I'm still recording. Okay, I'm still recording. So let's write the definition. It's k equals 0 to n. K times this expression here, so n, choose k. P to the k, 1 minus P, n minus k. So I want the first thing I want to do is notice that when k equals 0, this whole expression is 0. So we can just rewrite it to include this. K times, just the same expression. P to the k, 1 minus P, n minus k. Okay. So then the next step is I want to rewrite this k times n choose k. So I want to rewrite this. So we know that n choose k is n factorial over k factorial, n minus k factorial. So this k cancel out, and we end up with, let's also take on n out in front here, n minus 1 factorial, k minus 1 factorial, and then let's rewrite n minus k as n minus 1 minus k minus 1 factorial, which is equal to n times n minus 1, k minus 1 And then let's also take out a p from here. And so let's rewrite this entire expression as, from right space, k minus 1, n, we took out an n and we took out a p. And then we rewrote this thing, so n minus 1, k minus 1, p to the k minus 1. And then here we are going to rewrite this as n minus 1, same trick, minus k minus 1. So now we're going to replace k by itself, just minus 1. And then we're going to replace n. I mean, I guess we could realistically use different letters. So let's say that r is k minus 1. Yes. And then let's do m is n minus 1. So then let's do, this will be a summation from r equals 0, because that's k minus 1, to m. And then we're going to do here, crap, that's a mistake. Yeah, the point I'm trying to make is it'll look exactly the same as the expression which we had before, which we know sums up to 1. So therefore this is equal to np. Okay. Okay. A financial application. Is the recording? Yes. Suppose a fund manager outperforms the market in a given year with probability p, and that she underperforms the market with probability 1 minus p. She has a track record of 10 years and has outperformed the market in 8 of the 10 years. Moreover, performance in any 1 year is independent of performance in any other years. How likely is a track record as good as this if the fund manager had no skill, so that p equals 1/2? So she has no skill. Each year she has equal chance to outperform and underperform the market. So it's a binomial distribution. We're flipping the coin 10 times, and the probability that that she outperforms 8 out of 10 is greater than or equal to 8, or more than or equal to 8 out of 10. Okay, Poisson distribution. We say x has a Poisson distribution if probability that x equal to r is lambda to the power of r e to the minus lambda over r factorial. Expectation of x is lambda and variance of x equal to lambda. So in my class, the way we did this is we have a fisherman and he's fishing, and there's fish here, and there's an infinite number of fish, and he catches on average 1 fish per hour. So what is the distribution of how many fish the fisherman catches in 1 hour? So catches in 1 hour. So it's possible for the fisherman to catch 0 fish, or for the fisherman to catch an infinite number of fish. On average, he's going to catch lambda amount of fish. Yeah, that's the Poisson distribution. So as soon as you catch your first fish, you can try to keep fishing and catch as many as you can. So here's the proof. It's very similar to the binomial distribution. The expectation of x is equal to, again, this is r times the probability that x is equal to r, from r equals 0 to infinity. Then we substitute it in the definition. We are going to cancel this out to get r minus 1 factorial. Then we're going to take out a lambda to the front here. And then we're going to shift this over by 1. Since it's to infinity, there's infinite terms. We can do this easily. And then we just end up with lambda. So that's it for the first lecture. See you next time.